So my name's Shawn Roman. I'm the Vice President of Research and Development for Bovie Medical. And we've got a technology that's called J-Plasma. And I'm going to walk through what J-Plasma is and give you an overview of some of the things that we're working on from a development standpoint and from a research standpoint. And then they had asked me, since we do this every day with respect to developing new products, they'd asked me to kind of run through the product development process within a medical device company so that you guys get an understanding of the different steps that we go through to develop product. Okay? So please feel free to ask questions because I'm going to be asking you guys some questions along the way. So we'll just make this as interactive as possible. I'll ramble on for a little while and kind of give you guys the whole overview of the whole presentation, and then at the end we're going to bring in the actual product, the J-Plasma product, and we'll do a little bit of demonstration so you guys can get some hands-on with it and see how it works. Okay? So what I'm going to do is go through and give you an introduction to J-Plasma. And so we'll answer this question as to what is J-Plasma. But first, I'm going to take you back to some high school physics, some high school chemistry, some high school electrical engineering, and ask you guys some questions. So, what is electric current? Can anybody answer this question for me? Anyone? You got it? What? Yeah, you got it. So, perfect answer. You guys, the other class, real smart too. So they answered every single one of these questions. So that was good. So this is Eric, who's making a not so inconspicuous entrance. This is the product. We'll do a little demo later, like I said, when we're done. But the answer was correct that electric current is the flow of electric charge. So we'll talk a little bit about this real simple circuit, and then later on when we talk about what J-Plasma is, I'll give you an understanding then as to how this kind of all ties together. But if you guys remember, or in this very simple circuit, we've got a battery with a difference of potential or a difference of voltage, which causes electrons to flow from one side of the battery to the other. Anybody answer the question as to why we have the electrons flowing? We're showing them flowing in the direction that they're flowing in this diagram. Anyone? Man, see, I joke, the sales guys are going to get sick of hearing this joke, but because we've got some sales guys from Bovie here, and I use this presentation to do training for the sales guys, and nobody ever gets that answer right. So it's fun to be in here with a group of folks who get it. So I'm just going to keep raging on you guys all day. So yeah. So great. So like I said, we'll talk about this simple circuit diagram here briefly, and then when we talk about J-Plasma in more detail, I'll kind of bring you back to this circuit diagram. All right. So what's an ion? Can anybody answer this one for me? No one? Got it? Yeah, that's a good answer. So it's an atom or a molecule with that has a net electric charge. So like if you take a helium atom, for example, a neutral helium atom has 2 positive protons in the nucleus. It has 2 neutrons, and then it has 2 negatively charged electrons on these outer rings, right? And so a neutral helium atom, the number of electrons cancels out the number of protons, so you have no net electric charge. But if you give that helium atom enough energy, you can cause one of those electrons to leave, and then it'll have a net positive charge, right? And it becomes an ion at that point. So we'll talk a little bit about what we're doing here with helium as we discuss J-Plasma. So basically, this is what we're doing. We're ionizing helium gas and using that helium gas, ionized helium gas, to generate a plasma. All right. So what's a noble gas? Does anybody answer this question for me? Yeah. You got it. So if you guys remember, it's this column of elements in the periodic table, and they are gases that are characterized by full. They have their outer electron shells are full, so they have low chemical reactivity, and helium falls into this group, and that's one of the reasons why we use helium in this product. All right, and then so what is plasma? Can anybody answer this question for me? So plasma is typically referred to as the fourth state of matter. So if you take the example of water, for example, you start off with a solid in the form of ice, put some energy into that, you can turn it into a liquid, put a little bit more energy into that in the form of heat, you can turn it into a gas, and then you give it even more energy, and you can actually turn it into an electrically charged or ionized gas, which is what a plasma is. And so in the case of water, it takes a lot of energy to turn it into a plasma. In the case of helium, not so much. And we'll talk about the benefits of that in just a little bit. All right, so great job, great audience participation, some really smart folks. I appreciate you guys being able to answer some of those questions. It's good stuff. And I'll try to tie all this together as to why I'm asking you these questions as we talk about J plasma in a little bit more detail. All right, so what is J plasma? So with J plasma, basically what we are doing is we are using electrical energy to ionize helium and turn it into a helium plasma. So in this simple circuit down here, which I don't know if I've got a pointer on this thing or not, which doesn't look like I do. In this simple J plasma circuit, you can see that there's an inner electrode, and what we're doing is we have a helium pathway, and we pass helium over that electrode, and then we deliver electrical energy to that electrode, which gives enough energy to that helium gas to cause it to be ionized. And then when it becomes ionized, it becomes electrically conductive. So we effectively create a potential difference, like in that previous circuit diagram we talked about. We create a potential difference from the electrode to the patient that we use as a ground. And then using this now ionized helium gas, it becomes electrically conductive, and we can then conduct electricity from this electrode to the patient. All right? So we use this, it effectively becomes a flexible electrode, a flexible wire or gaseous electrode that extends from the electrode to the patient. And it allows us to do some really cool stuff. So basically we're using it to ablate or cut or coagulate soft tissue. And there are a lot of benefits associated with the way that we do that for the patients. So I said this earlier, really the big take-home message for J plasma, if you hear anything about J plasma today, very precise energy delivery, as well as very minimal thermal damage to surrounding tissue. So it allows you to do things like work directly on some vital structures, on or around some vital structures, without causing damage in places that you don't want to do damage. So as an example, we are able to remove endometriosis cells from fallopian tubes and from ovaries without causing infertility issues in patients that are still in childbearing years. All right, so we are giving surgeons a tool for being able to take care of those endometriotic lesions that they don't currently have today. They don't have an option for those patients today. All right? So any questions about what we're doing so far, where we're going with this? Yeah?
How long has this been around?
So this has been on the market for, it's about 15 months, so a little over a year. We've got a lot of good headwind and are starting to see like a big ramp in sales. But we've got a lot of potential applications for this that we're just starting to scratch the surface on. I'm going to touch on a little bit of that here shortly as to the different types of products we're working on, development projects that we're working on and some of the research that we're doing. Some pretty exciting stuff. Any other questions? All right. So if we keep going, so this is what J-Plasma looks like on the market today. Like I said, you're going to get a chance to get some hands-on here shortly. So we'll be cooking some eggs and cooking some chicken over there, so you get a chance to see what the ablation looks like and how to cut tissue with it. But basically, we have a couple of different electrical generators. And these generators deliver the electrical energy to the electrode we talked about that does the ionizing of the helium. And we have multiple hand pieces. We have a few different laparoscopic lengths, which you see on the right-hand side of the screen, as well as a handpiece that the surgeons will use for doing open procedures. And then we have a couple of different designs for these electrodes that are doing the energizing of the helium gas. And these electrodes, the different designs, serve to do different things. It's not just ionizing the gas. You use these to cut tissue with as well, and you get a very precise cutting effect. And again, we'll show you that as we get into the demo. So that's what the system looks like today. And in just a few slides, I'll be going over some of the new products that are launching actually as we speak, and we'll be launching in the near future. Okay. So we'll talk a little bit now about why we chose helium gas over another noble gas like argon. One of the things that we really like about helium is that it doesn't take much energy to ionize the helium atom. And that's a good thing because we want to minimize the amount of energy that we have to put into the system because we're trying to minimize the amount of energy that we're transferring to the patients, right? Good thing about it, very easy to initially ionize it, but once that first electron is off of the helium atom, the atom then holds on pretty strong to that second electron because you now have two positively charged protons in the nucleus and holding on pretty tight now to that negatively charged electron that's left. And so it effectively results in a current limiting, right? We talked about earlier that electric current is the flow of electrons. So we get a very consistent flow, or with the amount of energy that we're delivering, we know we're only going to be releasing a certain amount of electrons, so a certain amount of current. And that current is what translates into tissue damage, because as current flows through tissue, that's where you get tissue damage and killing of tissue cells. So those are some of the benefits of helium. The other benefit of helium is that it has a pretty high thermal conductivity. So we're ionizing just a small portion of this helium gas, and the remaining helium that's left is there basically bathing the site and cooling the site, so it helps again to minimize like tissue injury and help to keep the site cool. All right, any questions so far? All right, we'll keep going. Again, this is the take-home message. If you've heard anything about J-Plasma, it's very minimal thermal damage to the tissue. So what you're seeing here are histology slides looking at the amount of thermal injury compared to other typical energy modalities that are used, like CO2 laser, argon plasma, or monopolar electrosurgery. So, 0.147 millimeters versus a full millimeter in a typical monopolar electrosurgery setup. And this is just another slide to drive home that same message. Very minimal thermal injury. Basically what you're looking at here is if you treated an area and then took a cross-section, you could see how wide and how deep you went as far as thermal injury goes. And you can see J-Plasma there at the top, the little orange section up there. All right. So we talked a little bit about these electrodes earlier. We have a couple of different electrode designs. These electrodes are really dual purpose. They are there to deliver the electrical energy actually to the helium gas and ionize it to turn it into a plasma, but they also serve as a cutting instrument. So you can either extend or retract these blades or needles. And so when they're retracted, you can use it just to ablate tissue, or you can extend it and actually use it to cut tissue. It does a really effective job at that. It's really good at cutting tissue with very minimal thermal injury, very little charring, very little generation of smoke in the surgical procedure. All right, and I won't spend too much time on this slide. Really, the take-home message from this slide is that there's multiple different ways to make plasma. There are some benefits specific to the way that we make plasma that is going to be beneficial for us as we move into future applications. So we are a kind of remote discharge plasma versus like other types of plasmas which are local discharge. And this remote discharge actually will generate what we call radical, like oxygen and nitrogen radical species. And in a nutshell, basically, we are operating and we are activating J plasma in air, right? So the energy that comes from that plasma generation is interacting with the oxygen and nitrogen in the air, and it generates things like nitric oxide and like hydrogen peroxide and things like that. And those radical species that are generated through this activation of plasma in air actually do some really good things with respect to killing cancer cells, killing bacteria, killing viruses. So those are some of the things that we're looking at for future applications of J plasma. All right, this is a boring slide, so we won't spend too much time here. There's a couple of different features on the generators that give us different ways to, or different methods or different features of the plasma. So we can adjust the amount of energy we give, and we can adjust the amount of helium flow that we have. And so the higher helium flow rates, more precise beam, lower flow rates, you get more of a turbulent flow, so you get kind of more of a fulgurative effect. These are some of the applications that we're currently using J plasma for. This list is growing every day, but we've talked a little bit about the use of J plasma in endometriosis. It's good for breast capsule scoring, breast augmentation procedures, some abdominoplasty. We have some surgeons that are currently using this product actually off-label for dermal resurfacing because it does a really good job of reducing wrinkles on the face, like to replace kind of like a laser treatment that they use for reducing wrinkles. So lots and lots of different applications for J plasma. So this is where we are today, but we have a ton of other applications that we're looking at and investigating. So we're really starting to venture into the cardiac space now, working with some cardiac surgeons on using J plasma for taking down the intramammary arteries, for pericardial fat dissection, for dissecting the pericardium. We have a surgeon that is doing a lot of pediatric cardiac cases where they see a lot of like scar tissue or adhesions because they're going into these patients multiple times. So J plasma, very good in applications like that. Mr. Nicholson, who presented during lunch, mentioned Dr. Vip Patel, who is basically across the street at Florida Hospital. We're working with him in the urology space to develop J plasma for radical prostatectomy procedures, as well as looking at lymphocyte reduction. And I have a whole slide associated with that, so I'll get into a little bit more detail on that here in just a little bit. And I mentioned killing cancer cells, killing bacteria. So looking at using J plasma for the treatment of chronic wounds and for sterilization effects, and hopefully to have as a product for bulk dissection of cancer or for cancer treatment down the road. All right. You guys have any questions? All right. So, yeah, go ahead. How do I answer this question?
So, I'm Eric, by the way. I'm one of the engineers for that question. We spoke to a lot of helium companies. Technically, everything's at a shortage: oil, gas, helium. Helium is a natural byproduct of natural gas well production. So, we had a reduction a number of years ago because they were tapping off wells. Well, since then, so we're also
No, you got it. You can hear it.
check, check, check. Okay. So what they're doing is they're opening new wells and they're producing more helium. And a lot of the world was getting a lot of the major supply of helium from the U.S. had a huge stockpile of it, and they were shipping it out. And they decided a number of years ago, we're not going to keep any more helium, and they were keeping it. So that created the shortage that everyone was a big problem about. But either way, long story short, for medical applications, helium isn't only used in this product. Helium is used in MRIs. Are we going to stop doing MRIs? No. So there's a lot of things that medical applications have the trump card for. So helium will be used, at least for our product and other medical products. They get the trump card to use helium first and foremost. And with regard to our product, I don't know if any of you can see the little orange tank that's right underneath there. That little orange tank will last a surgeon who does an average number of surgeries per week about 6 months. That's how little helium this project uses. So MRIs probably use a canister about this big. They refill it every month. So we're a blip on the radar of helium companies. Yeah. Does that answer your question?
Yeah, so short answer is it doesn't. It's not that, like, we're okay. Yeah. Yeah. So what we'll do now is go through and kind of give you guys an understanding of some of the products that we're working on and some of the research that we're doing, and then we'll transition into giving you an understanding of what the product development process looks like within a medical device company. All right. And then I'll stop talking and we'll do the fun stuff of actually playing with the product. Okay?